para cromatografía iónica. Es el referente dentro de la cromatografía iónica, donde nuestra experiencia es sin duda una de nuestras insignias. Asimismo, distribuimos los equipos automatizados de extracción en fase sólida y extracción acelerada con disolventes. CEM es nuestra representada de equipos por microondas para digestión, extracción y síntesis, así como equipos para control de procesos, rápidos, precisos, seguros y reproducibles. En búsqueda constante de la mejora continua, CEM acaba de presentar su nueva mufla Phoenix Black, la mufla más rápida del mercado. Teledyne Isco es un referente en cromatografía flash y preparativa y bombas de jeringa de alta precisión. Y Nippon es nuestra representada japonesa que se dedica exclusivamente al análisis de mercurio en cualquier matriz, tanto muestras sólidas, líquidas como gaseosas. UCT es nuestra representada de consumibles para extracción en fase sólida, catchers, cleanups, sorbentes diversos, así como concentradores de muestras y manifolds, entre otros muchos productos. Y en el Departamento de Biotecnología disponemos de una amplia gama de instrumentos dedicados al sector de la biotecnología, como pueden ser contadores de partículas, lectores de absorbancia, luminiscencia y fluorescencia, kits de extracción de ADN, sistemas de cultivo, bioreactores y analizadores bioquímicos, entre otras cosas. Por último, el Departamento de Higiene se focaliza en equipos de evaluación de riesgos físicos, químicos y biológicos, enfocados a la prevención de riesgos laborales. Entre ellos encontramos bombas y accesorios de muestreo, muestreadores de polvo, medidores micro y nanopartículas, monitorización de gases y tubos colorimétricos. Y ahora, sin más, voy a dar paso a Philip Moss, Sales Manager Europeo de Teledyne Isco, que es quien nos va a impartir el webinar sobre purificación. Hi, Philip.
Hello. Can you hear me?
Yes, I'm going to give you the control.
Oh, good. Thank you.
You can ask for the control because I don't know. Sorry.
Okay.
Can you ask for it?
How do I do that? Sorry. No. Is there a particular button I should press for that? Sorry. No.
Philip, Philip, you have a
Philip,
button
in
the bar that you
Yes.
You can read a request control.
Which?
So if you move your mouse on the presentation, you can see a button that it says request control. Can you see it? It's close to the Hangout button.
The hand.
Yeah, next to the hand on
Is
the right side.
More actions.
No, more on the right side.
Show participants.
The other one.
There are no more.
Oh, okay, so you don't have it.
So Philip, don't worry, I can pass the slides.
Yeah.
Okay. Let me just carry on, and I'll ask you to change the slides. That's probably the best, rather than wasting any more time. Good afternoon. Sorry, it's as you probably understand. I hope you can hear me. My name's Philip Moss. I work for Teledyne Isco for the last 10 years. You may be able to tell from my accent I'm based in the UK, although Teledyne Isco is a US company. So next slide, please. And click again if you wouldn't mind. Thank you. So basically, just an outline of the talk. I'm just going to briefly introduce the company, which I think has already been done a little bit, and then talk a little bit about chromatography, thin layer chromatography, TLC, glass columns, and then automated chromatography. And then move on to the features and benefits of automated flash chromatography, talk about the Teledyne flash chromatography products, and then do a sort of comparison of flash and preparative chromatography and the places that they have, and then a little introduction on the preparative side as well. So next slide, please. So yeah, Teledyne is a US company. We're based in Lincoln, Nebraska, which is that red spot in the middle. We also have a separate company now that produces pumps there over on the East Coast. Our products are mainly laboratory and process instrumentation, but the focus of today is really on liquid chromatography separations. We also manufacture in the laboratory products. We make pumps as well, but as I said, today's focus is liquid chromatography. Next slide, please. These are our purification products. We'll talk a lot more about them later. We have the next gen, which is the flash purification product on the right-hand side. The Easy Prep, which is a hybrid system, flash and preparative chromatography, and then a dedicated prep system on the left-hand side. That's the AccuPrep HP 150. Next slide, please. We have a lot of our customers are using our systems for research or small-scale purification, but we do have a larger scale purification flash system called the Torrent, and that's on the picture there. Next slide, thank you. Just to quickly look at the other products, we have fraction collectors. Teledyne has been making fraction collectors since 1959. The picture you can see there is the Foxy, which is fraction something XY, being X moving on the X and the Y axis. We have preparative HPLC columns and also ready step columns. Thank you, sorry. You want to change the slide again, please? Thanks. Just a quick mention, as I said, we manufacture pumps. These are used in our flash chromatography systems, but they're also produced for specific chemical processes, catalysis, flow chemistry, reaction chemistry, and applications in the petroleum and polymer industry. So, but we're not talking about those today. Next slide, please. So moving on to the main purpose of today, which is chromatography and separations. Just want to talk a little bit first about what the definitions of liquid chromatography. Next slide, please. So chromatography is a separation of, it's a laboratory technique for the separation of mixtures. You dissolve your mixture in a liquid, which is called the mobile phase, and then you pump it or pour it through a column, which is packed with a material which is known as the stationary phase. In most chromatography, this is silica, although there are some variations to that. People can use alumina as a material. As I said, the mobile phase, the liquid that's pumping through the silica is the liquid. The stationary phase is the media, and the chromatography is the sort of interaction between the sample, which is in the mobile phase, and the stationary phase, depending on charge. And we'll talk about normal phase and reverse phase chromatography as well, but normal phase in a little bit. So next slide, thank you. Liquid chromatography comes in a number of forms. Thin layer chromatography, this is used a lot for identification or seeing if you can get a separation. It's used a lot in chemistry labs. Flash chromatography, which is a traditional sort of purification chromatography for crude mixtures, separations. And then you've got high performance liquid chromatography, which can be analytical or preparative. Our focus is prep. And then there are some newer forms of liquid chromatography, UHPLC or UPLC, which is ultra high performance or ultra high pressure liquid chromatography. That is in italics because it's not something that we're going to be talking about today. We're focusing on purification, which really uses thin TLC, flash, and HPLC. Next slide, thank you. Just to show a picture of a typical sort of traditional flash column chromatography setup, which is glass column, and these come in different sizes with somebody standing there at the back pouring the liquid into the top of the column. That's how you introduce the sample. That's how you introduce the solvent, which passes the sample down the column and makes the separation. Next slide. Customers or people using chromatography would be typically working in a number of areas, but typically they can split these into synthetic compounds and natural products. With synthetic compounds, it'd be pharmaceuticals or chemicals or agrochemicals. Typically, people know what they're working with, or they're trying to produce something by synthesis, by flow chemistry or microwave synthesis or traditional synthesis, and then are then trying to purify it, so they know what they're looking for. Natural products is a bit different. Typically you're trying to extract biologically or chemically active compounds from a plant material, which is a complex mixture, and sometimes you don't even know what it is that you're looking for. So the chromatography can take a different form, or the techniques used can be different. Next slide, please. Okay, so looking at glass chromatography, column chromatography, basically you pour the sample into the column at the top left-hand side there. You wet the column first, or you can use air to pack the column, and then you add the sample, and then you pour the solvent in to make the separation, and then you stand there collecting the fractions, which is a fairly tedious process. And then at the end of that, you have to TLC the fractions to see which of the fractions contains the compound that you're interested in. Next slide, please. As I mentioned earlier, there are different types of chromatography. We have normal phase, which is probably the one that's most commonly used in flash chromatography. And normal phase refers to the fact that the stationary phase is polar, and that's silica is the stationary phase typically, or it can be alumina, and the solvents that you're using to introduce the sample and wash through the stationary phase are non-polar or much less polar, and these would be petroleum ether, hexane, cyclohexane, and then you can increase the polarity by moving to things like dichloromethane. So this is commonly used in flash because silica is quite inexpensive. So next slide, please. Reverse phase came along later. That's why I say a newer type of column, but it's been around since the 1970s or 1980s. It's reverse phase because in this case, the stationary phase is non-polar and the mobile phase is more polar, hence the reverse of normal phase. It's still basically the packing material is silica, but you have coated the silica with a non-polar sort of coating, which is typically things you'll hear of things called C18, which is a non-polar chained molecule that you attach to the silica to shield it to make it non-polar. And then the typically polar solvents you'll use to introduce the sample would be water is the most common, and then to decrease the polarity you would use methanol or acetonitrile or THF tetrahydrofuran. Next slide, please. Now, thin layer chromatography is used a lot in chemistry labs to identify, to see if you're getting a separation. So you would take a sample or spot a little bit onto a plate, and then put that TLC plate in some solvent, and then see how the spots move relative to the as the solvent is drawn up the plate, how the spots move relative to the solvent line. Next slide, please. The reason why people are doing TLC plates is it's a relatively quick method to determine how a reaction is going, because you can look to see if where the product spots are, or the substrates or the impurities. And it's also a very quick way to develop methods for flash chromatography. So before you introduce your sample onto the glass column or the column, you do the TLC to identify, you know, a method or solvent or stationary phase that will give you the best chance of a separation. Next slide, please. Okay, so I've mentioned that the TLC is effectively used as a method development tool for column chromatography. The reason this works is that when you introduce a sample onto a column, the same as when you introduce a sample onto a TLC plate, it will migrate depending on the interaction between the normal phase, between the stationary phase and the mobile phase. How that migration happens on the TLC plate is the same as on the glass column. So with the TLC plate, you calculate what they call RF values, which are retention factors of the spots, sample spots relative to the solvent. And these RF values basically correlate with what column volume. So, and it's a kind of inverse correlation, but basically you can work out from the TLC plate how many column volumes you can use to wash your sample through the column. Next slide, please. Okay, so glass columns chromatography has been, if you like, the established method for many years, but it has disadvantages. Firstly, it's very time consuming. Because the person has to stand there and introduce the sample and then collect all the fractions. You can only use one sort of solvent mixture at a time. So you would, you know, if you're working with one solvent and one stationary phase, unless you're not changing the polarity so it can take a long time for the samples to wash through. When the samples are collected, you don't know which samples contain your compound of interest, so you have to TLC every fraction. And basically, it's not actually that safe. Silica's fairly nasty stuff. It's fairly hazardous to deal with and handle. The solvents you're using are not very nice, typically in normal phase. So there's, and then basically trying to pour solvent into the top of the column, especially if it's DCM, which is very heavy, it's just, there's a lot of safety implications. And also there's a lot of skill involved in packing a glass chromatography column and doing it properly. So there are sort of lots of disadvantages with the traditional methods. Next slide, please. Okay, so moving on to the automation of flash chromatography. Next slide, please. Basically, how are we automating the system? What we're doing is that the key things are that we're introducing a pump, so you can pump the sample through the column and the solvent much quicker than using gravity or some kind of negative air pressure. We've got something called a gradient former, which is basically allowing you to mix solvents together so you can adjust the polarity. Then you can introduce the sample using a valve, either by a liquid introduction or a solid introduction with some kind of pre-packed cartridge. You then have a separation column, and then the next part of the sort of improvement, if you like, is the detector, because the detector, you can look for activity by detect activity, which will tell you when things are washing through the column. So you can just collect those fractions if the detector is talking to the fraction collector. And then all of this is controlled by software, which is simple to use. Next slide, please. Okay, so looking at, I'm telling you there are benefits of automated chromatography, so just trying to illustrate that in some way. Next slide, please. Okay, if you can, just click it through to the, thank you. Basically, this is to try and illustrate the benefits, we try to recreate a sort of typical column separation on a packed column, trying to separate these two amides. And this is showing that what the TLC plate looks like with 30% ethyl acetate in heptane, and you'll see the two amides spots are fairly closely eluted. The little black lines at the bottom are where you introduce the sample, and the black line at the top is where the solvent front got to at the end of the separation. Next slide, please. So we sort of simulated an open column purification. If you could just click to bring up the lines, please. Just thank you. And again, thanks.
Sorry.
Okay. Basically, on the left-hand side, you'll show a separation in 30% ethyl acetate. And what you're showing, and this is just a silica 12-gram column with a mixture of 30% ethyl acetate, and you're showing that at the end of the separation, we've collected a number of fractions, but 3 of them are pure compound A, 4 of them are pure compound B, but we have 3 fractions there that contain a mixture of both. On the second one in the middle, we're using 25% ethyl acetate. In this case, there are 11 fractions. The separation is slightly better, but there's still one of the fractions that is a mixture of A and B. Finally, if we move to the third one, which is the 20% ethyl acetate, we've now got complete separation. So we have 11 pure fractions of compound A and 11 pure fractions of compound B. But we've generated 22 fractions, and this has probably taken a lot longer. Next slide, please. So just comparing that with alternative approaches that you could try, you could use a step gradient, which is possible with a glass column, which is where you would change the, introduce different concentrations of solvent in steps, basically. And by doing that, you can reduce the number of fractions to 15, but collect 6 pure A and 6 pure B. But then finally, we did the same thing again with a linear gradient, where we gradually changed the gradient from hexane to heptane to ethyl acetate. That's this blue line here gradually going up. And in that case, we have collected 16 fractions, of which 7 are pure A and 7 are pure B. So to try to summarize all of this, next slide, please. Okay, in the isocratic separation, which is the glass column with the fixed solvent mixture, we collected 22 fractions. We used 900 milliliters of solvent, and it took 30 minutes to do the purification. In the step elution, which is something that you could do on a glass column, you could reduce the number of fractions to 15. You could reduce the amount of solvent slightly to 840 mils, but the time to purification, 20 to 28 minutes, is pretty similar. But if you make an optimized gradient, which is a gradual change of the solvent mixture, you get 16 fractions. You only use 660 mils of solvent, which is 30% approximately less solvent. And the time taken is also just over 20 minutes. So once again, about 30% less. But this is with a small column. If you scale this up to a large column, the time savings, it can be enormous. Next slide, please. So just to look at a typical automated flash system, this happens to be our older model, but the principles are still the same. You've got solvents that you can introduce and some kind of pumping system, mixing system. So we've got either 2 or 4 solvents you can introduce. You've then got a way to load the sample, which is either a sample loading cartridge or some kind of liquid injection. There's an automated injection valve to allow the sample to be introduced and to allow you to wash the column first. Then you have the sample separation column, which can come in. These are pre-packed columns, which come in different sizes. So these fit here. So you introduce the sample, it goes through the column, then it goes to an integrated detector, which is usually a UV or UV visible detector, and then on to the fraction collector. And all of this is controlled by a sort of inbuilt computer with a touch screen. So it's a sort of fairly compact system, but it's fully controlled, self-contained and controlled from its own software. Next slide, please. This is just showing, our new system, which is the next gen, and it's our 5th generation instrument. And what I'm showing here is, from left to right, the various versions of systems that have come to this. The one on the left, the SG100C, is really basically a pumping system with our old fraction collector, because we've been making fraction collector for 50 years. So that was the first version, and then there was a second version, and then in the third version, the big change came when it all became computer controlled. The other systems were manually controlled. You controlled the pump, you manually controlled the fraction collector. But since 2007, we've been using a computer controlled system with a touch screen. And this is, say, the next gen on the right is the latest version. Next slide, please. Okay, so just to give an overview of our system, the next gen system, which is I've said 6th generation here, actually it's 5th generation, forgive the mistake. Next slide, please. So there are basically different versions of this. It's kind of like when you buy a car, you get different features and accessories. You choose the version you want. There's the 300, the 300 plus, and the next gen. Next slide, please. Okay, so standard features on these systems is you've got the touch screen and the sort of full control of the computer. Flow rate up to 300 mils a minute. The flow rate is basically varies depending on the size of the column that you're using for the separation. The maximum pressure on these systems is now 20 bar. Typically with a glass column, the maximum pressure was 3 or 4 bar. By going to higher pressures, you can pack the columns with smaller particle-sized silica, which can improve the separation. We've got what's called a solid load valve, which improves the injection. But you could also wash the sample and automatically inject the sample. You can wash the column first. We have these radio frequency identification system, RFID, which is used on the racks and also for reading the columns, so that when you load a column, the system automatically loads the parameters for the column. We've got active solvent and waste level sensing. There's a lot of safety features. I'll talk a bit more about that in a minute. And then the system can generate binary gradients, so it can mix 2 solvents together in different compositions. And you do have the option to add a 3rd solvent as a modifier, because when you're working with silica, sometimes the sample can interact with the silica and it sort of gets very sticky, and you get kind of tailing effects and poor separation. So by adding acids or bases, you can improve the quality of the separation. Finally, you've got a choice of 4 solvents. So you can make a mixture between 2 and then change the mixture between the 2nd and the 3rd solvent. Next slide, please. Okay, so the system, one of the key things about getting people to use these kind of systems was making them simple and easy to use. And this is really down to the software. If the software is complex, people won't use the system, or people can make mistakes. So we've tried very hard to make it very simple. Next slide, please. This is what the front screen looks like. We've tried to keep not too many things on there. You'll notice there's a little arrow here which says start, and basically you would press that to start a run. On the left here, you've got the absorption display of the UV. This blue line is the gradient going up from 0 to, well, in this case, 100% of this second solvent, typically ethyl acetate. The length of the run is 8 minutes, but you can also display this run in column volumes, which chemists can prefer. And then you select things like, you can vary that gradient, and you can change everything while the system is running as well. Next slide, please. At the end of all of this, what you hope to get is a nice separation. And of course, I've picked a nice one to show you. In this case, you'll see there's 3 peaks have been, this is the report you get at the end. You've got 3 peaks showing here, and the coloured lines underneath indicate that this peak is collected in these coloured fractions, and it's found in, this is a map of the fraction collector. It tells you where the fractions are. The second peak is a sort of greeny colour, greeny blue, and the compounds are there. And the third peak is the blue, dark blue, and they're held in positions 16 to 19 on the fraction collector. So that's that you get that report, and then there's other information you get in the report as well. Next slide, please. Okay, I mentioned about sample loading. There's different ways to do that. Because we have this valve in the system as an option, you can basically wash the column first, or which is, can improve the separation. But if you're using other kinds of columns like reverse phase columns, it's important to wash and activate the C18 chains by washing in an organic solvent and then a water, and also making sure the column is clean. So you're washing and pre-equilibrating the column, and then you can load the sample with a liquid injection if your sample is soluble in the initial solvents that you're using for the separation, or you can load the sample by using a solid sample loading. And in the picture, what you can see at the bottom right hand side is the separation column under the screen, but up above it, this is the pre-column, which is just a little cartridge that you can pack with some silica on which you absorbed your sample. And when you do your sample introduction, the flow goes through the pre-column cartridge onto the separation column. The valve that we're using has a self-cleaning protocol. This is very important to make sure that no sample is left over, to contaminate a separation that somebody does later on. Next slide, please. We have a pumping system to deliver the solvents. Basically, it's important with the pumping system to be accurate. So when you are mixing together solvents, the accuracy of the mixture or the gradient is better than 1%, which is very useful and reproducible. The pumps can pump precisely from 0% of one solvent up to 100%. And then they can pump many different solvents. And the reason we're mentioning methylene chloride, or DCM, as it's sometimes called, is because it's very dense, and a lot of pumping systems can't cope with that very easily. And when I say pump from any solvent location, it means you can keep the solvents on the floor below the instrument, even with DCM, which is dense, and the pumps are powerful enough to pull the DCM into the instrument. The other thing with having a pumping system is not to introduce a lot of noise into the laboratory. Next slide, please. So as I said, you can use a 4-solvent mixture you've got a 4-solvent choice. You can make a mixture of 2 solvents and add the 3rd solvent. You can change which solvents you're using to make that 2-solvent mixture during the run in the programming. And as I say, you can automatically monitor the solvents, so you know the level. And it's very important for safety reasons. We're using highly flammable solvents here, potentially up to flow rates of 300 mils per minute. So this automatic level sensing is vitally important as a safety feature, because you want to put your sample on, let it separate, and walk away and do something else. Next slide, please. The systems can accept columns up to 330 grams in size. That's the largest of the standard columns we pack. The size of the column dictates how much sample that you can load on. Depending on the difficulty of the separation, you could load up to 10% of sample, which means theoretically you could load 33 grams of sample. And it also depends on the purity that you want to get. Now, as I said, the system can only accept columns up to 330 grams in size because that's the biggest one that fits. But what the picture here is showing is an adapter that you can put alongside the system to, if you do occasionally want to run a larger column up to 1.5 kilos, which is shown there, with this adapter that you can use. Next slide, please. Safety features, as I mentioned, are very important. We're working with flammable solvents, with lots of flammable vapors floating around, so it's important to be very careful with this. So we have automatic solvent level sensing, as mentioned. The tubing, the connecting tubing in there is anti-static, because what you don't want is a buildup of static electricity and a spark. Cause that would maybe ignite any vapor that's around. There's safety feature. You can set the pressure limit, and the different columns have different pressure limits, so the system automatically sets that. There is a vapor sensor which will shut the system down if there's a leak, because it will smell the vapor. There is also a fraction collector enclosure option. The picture on the left is showing a perspex enclosure over the fraction collector, which if you put on there, and then you can connect some kind of negative pump to the back of the instrument to pull away any excess vapor. Next slide, please. Oh, can you check? Oh, thank you. And again, so we're talking about detection here. So we have different options: UV visible, evaporative light scattering, and mass spec. Next slide, please. Okay, so this is, as I mentioned, there's the different choices. This is showing the different instruments again, and on the right-hand side, we're showing the mass spec detector, which all the other detectors fit inside the box. The mass spec detector, if you choose that, has to sit alongside because it's too big to go inside the instrument. Next slide, please. And again, so we took UV first. So we have variable wavelength UV from 200 to 400 nanometers, or we can have an option of going to 800 nanometers, which is UV visible, which is useful for natural products and dye stuffs. The software allows you to change the wavelength during the run. You have 2 wavelengths. You can control the fraction collector. So if you know your compound absorbs at 2 wavelengths, you can monitor both and use it to collect your samples. We have something called all wavelength, which I'll talk about in a minute. We also have something called automatic baseline correction. So this is if your sample absorbs at the UV at the same wavelength as one of the solvents you're using, you can have a problem detecting it. But the baseline correction can be used to remove the effect of the solvent, which could be varying depending on the gradient that you're mixing the solvents together. And then you have purity indicators where you can ratio together different wavelengths to try and get an indication of if your sample is actually pure or not. Next slide, please. Okay, so just talking about all wavelength detection, in this particular case, this compound here is a catechin or caffeine mixture. The red line that you're seeing on the picture is the customer had selected 254 nanometers as the wavelength they wanted to run. And you'll see on the red line, there's actually 2 peaks there. They're not resolved. So it suggests there's two compounds there, which are actually now with the all wavelength detection, what we're doing is scanning across different wavelengths and averaging them together to make a combined signal. And what this enables you to do is pick up if there's any activity on one of the wavelengths other than 254. And in this case, the all wavelength averaging signal, the green trace, is showing that there are actually 3 compounds there. And because both of these are controlling the fraction collector, you are seeing a collection of 3 compounds. Next slide, please. Evaporative light scattering detectors, ELSD. These are useful if your sample doesn't have a chromophore. With UV, it only works if your sample has a chromophore. Evaporative light scattering evaporates the solvent and then detects the particles of sample. So it doesn't rely on a chromophore to do the detection. It can be integrated into the system. There is a limitation, and the limitation is that the analyte has to be less volatile than the mobile phase. And applications where this can be useful are things like polymers, sugars, carbohydrates, and steroids and detergents. A lot of these compounds don't have UV chromophores. Next slide, please. Okay, this is just showing a separation. I think it's a ribofuranose compound. It's a sugar. What you're seeing is a separation. The red line is the UV, and you'll see there's a peak at 3 minutes and a peak at 5 minutes, but there's nothing detected at between 8 and 10 minutes on the red line. The green line is the evaporative light scattering detector, and you'll see there's a big peak picked up on the green line, and that's the compound of interest, and it would not be detected on UV because there's no absorbance there. The blue line, by the way, is the gradient, which is gradually changing up to 100% B. Next slide, please. Right, mass spec. We can connect a mass spec to the instrument, well, to all of our instruments. The software is fully integrated, and what this enables you to do is to make your purifications using mass directed, so you can purify and collect very specific just masses of interest. So and you can use this mass spec in combination with UV and evaporative light scattering. Next slide, please. So just to talk about there's 2 models basically, but the difference is really the mass range. With the Model S, you can collect masses up to 1200, and the L is for larger range, and larger range is up to 2000. So perhaps if you're working with peptides, the Model L would be the one to go with. It's a single quadrupole machine, and it can use positive or negative ionization to do the detection, and can automatically switch between the 2. The system uses electrospray or APCI as the modes of detection. There's 2 options. Electrospray is the most common, and it's probably used by 90% of the people who are working with liquid chromatography mass spec. You can also use the system as an aside for direct injection for your development of method, or even for people who've got the system can use it for reaction monitoring as a kind of flow injection system, as a sort of secondary application of the system. Next slide, please. Okay, so the benefits of mass spec. You can determine the presence of a co-eluting impurity. You can have something that looks like a nice peak on UV, but if you got a mass spec there, you could see the masses of what's in that peak, and that could tell you that there's something else that's not separated. You can use the mass spec to collect up to 6 different masses. You just select the masses you want, and it only collects if it sees those masses. If you've selected specific masses and the system has collected them and the response of those masses decreases, it will automatically stop the run. So that will save on solvent and time. If you have the mass spec, it saves a lot of times after the run. With UV, you collect fewer fractions with no detection, but you still have to maybe TLC or run them on the mass spec or the NMR to determine which fractions are the compound that you want and whether those fractions are pure or not. Now, for natural product chemists, they can collect over a mass range, so they can eliminate unwanted masses, you know, so because with natural products you often don't know what the compound is, but you know it's within a range. So it's very useful to be able to use the range to sort of do fractionate your sample with natural products. Next slide, please. So just to show an application of that, this is something that we're using on the system, which is a combination of what we call wide polarity range chromatography to screen columns, and also show how mass spec can be useful as well. And this is working with this example with natural products or a complex mixture. And what you're doing is you don't know, the assumption is you don't know which column's going to best separate your compound, and also which solvents are going to work the best. So basically you can use like a screen of different columns and just run them using this wide polarity gradient. And you start with the weak solvent and then use a succession of stronger solvents to elute the compounds. So you can you know, you can try out different solvents depending on the polarity, and you can screen different columns, you know, silica, C18, alumina, quite quickly to see which is the one that you want, and you can use the mass spec to pick out specific compounds. Next slide, please. Now, I'm not showing all the slides here, but the example here is capsicum, which is obviously comes from chili pepper. It's basically, in this particular case, we screened the sample using a gradient from hexane to ethyl acetate, and then a second gradient from ethyl acetate to methanol, and then a third gradient from methanol to water. So you're running the column across a wide range of polarities. The compound, in this case, capsicum peak that you're getting is coming off at about 20 minutes, and that's the peak that's shown with the mass shown at the bottom, which is 306. But what you're seeing there is that you're getting some separation on the alumina column, but the peak is not actually pure. And there are actually more than one types of capsicum, so you're getting some separation of the capsicum, but not separating the different types. By the way, this was also run on silica column and on a diol column, and the results from that were quite poor. So next slide, please. So the same screening was done of the same sample, but this case on a C18 column. In this case, the gradient is going from polar to less polar solvent. You're going water, methanol, DCM. And what you're seeing at about 20 minutes is a peak coming off. Well, there's actually two peaks which are not resolved from each other, and these are two different members of the capsicum family. So you're getting some resolution of the capsicum, but you're not getting that being resolved from other impurities. So moving on to the next slide. So we had some separation with the alumina column in terms of better purity, but the capsicums were not resolved. With the C18, the capsicums started to resolve, but the capsicums were not separated from the impurities. So the plan here now is to do a two-stage separation. You run the capsicum first on an alumina column, and then collect the fractions, and then do a second purification on a C18 column. So in this case, next slide is going to show that the C18 column is run as the second separation. In this case, we're only running a gradient from methanol to water because we know that the capsicums elute in the methanol. And what we're seeing here is the start of we're getting some separation actually between three capsicum peaks. They're not fully resolved, but the capsicums are pretty well resolved from the impurities. So once you've got that far, you could then do a final purification on preparative HPLC, because the thing with Flash is it might purify to 80 or 90% pure. Next slide, please. So in terms of Flash, if if you have interest in that, I would recommend, and TLC, this book, it's a guidebook for working with different columns, for converting from TLC to Flash, and making suggestions of what columns work with different compounds. This is downloadable from our website, or you can get a hard copy. I'm sure Vertex can help you supply you with that. Next slide, please. Moving on, preparative HPLC versus Flash. Both can be used for purification, but which should you use in which situation? So next slide, please. So the consideration here is you're trying to purify a mixture of compounds. How much mixture do you have in terms of grams or milligrams? What's the relative concentration of your target? So you could have 1 gram of crude material, but only 10 micrograms of your target, or you'd have 1 gram and 100 milligrams. How difficult is the separation, and what's the final purity required? Next slide, please. A preparative HPLC system setup. I don't know whether you can remember, I showed you a slide of a Flash setup, but they're basically very similar. You've got solvents, pumping system, sample introduction, but with prep it's always liquid injection, a separation column and a detector, and then you can sometimes have different types of software involved with the prep LC. Next slide, please. So looking at the differences between the two, if you just click your way through this one, that was just to show the different things. Thank you. With Flash, obviously we're working at low pressure. The columns are lower efficiency than prep. They're using larger particle size. They are cheaper and they are disposable. And the focus with Flash tends to be on crude purification, but speed. You can run the Flash systems at high flow rates and you can load large amounts of material. And Flash is typically silica as the most common type of Flash, but there are different phases available. Prep, you are working at high pressure, so HPLC, high performance or high pressure liquid chromatography. The columns are much more efficient, so you will get better resolution. This is because they are smaller particle size. The columns are massively more expensive, I would say, but they are reusable. Prep, the focus is on analysis and higher purity and quantitation typically. The columns work at lower flows and you can load a lot less sample than you can on Flash. And typically prep uses modified silica C18, but you can pack the columns with different things. Next slide, please. The advantages of prep, you've got higher resolving power. You can get a lot more information from the detectors because of the resolution in terms of quantitation and analysis. And there are many stationary phases or different types of columns available to help you get maximum purity and maximum recovery. Next slide, please. The advantages of Flash, as I say, speed. You purify milligrams to grams of material. You can quickly remove the majority of impurities in one run. The operating costs are much lower than HPLC, so the acquisition is cheaper to buy a system. You can load more material on the column. The costs of the columns are much less, and the method development time for Flash is typically much less than with prep. So what should we use if you're doing a purification? Next slide, please. Well, the conclusion really, and this is what most people are doing, is that you use a combination of Flash and prep LC. With Flash, you've got high capacity, so you can remove a bulk of the impurities and other interferences and maybe get to 80 or 90% pure. So when you do that, you have much less material left, and you've increased the concentration of the compound of interest, which you would then, or could then, put to preparative HPLC to make a final purification. Next slide, please. So looking at our systems very briefly, because I'm conscious of the time, the AccuPrep is our dedicated prep system. flow rate to up to 150 mils a minute. It looks, you'll see, very similar to the Flash systems, and it's controlled in the software is very, very similar. So a lot of people find it who don't normally use preparative HPLC are very comfortable using this system because they're familiar with our Flash system. It's touchscreen operation. You can, and unusually for a prep system, you can change things during the run. You can change the gradient. You can change the solvents. You have the choice of all of the detection options that we've previously mentioned. Next slide, please. The software, as mentioned, is easy to use. We have the radio frequency racks, so that's a safety feature, so you know which racks are in the system. You've got the automatic solvent monitoring system. It's a binary gradient system. It has 2 pumps, but you have a choice of different solvents, 3A solvents or 3B solvent, and the system has a very small footprint. Next slide, please. This is the specification. Basically, flow rate up to 150 mils a minute, pressure up to 6,000 psi. In reality, what that means is you can work with columns up to 5 micron silica and with columns up to 50 millimeter diameter. That's the typical range of this system if you're working in optimal chromatography conditions. Next slide, please. There's different hardware options with the prep system. We have automation options, so for sample introduction, because it's liquid injection. There's a column selection valve. You can have different columns connected, so you can choose different which column you want to use for which separation. You can choose to direct the waste from each separation to a different vessel. Some people want to do that just in case something goes wrong. Large volume sample load pump. This is used as an alternative to the autosampler for injecting peptide samples, which tend to be very dilute. Third solvent modifier pump is just a pump for adding modifier to change the pH of your mobile phases to acid or to base to improve the separation. Funnel racks, because you can collect large samples. You can have funnels connected to bottles, and you've got different size racks to inject the samples, and racks now to enable you to inject very small amounts of samples. This is this high recovery vials, and you can now seal the samples as well to stop evaporation. Next slide, please. This is just talking about the different types of sample introduction. We have autosamplers, and we have something called an auto injector, which basically means you don't have the option to inject more than one sample, but you can inject that one sample multiple times. So typically with prep HPLC, the capacity of the column means you cannot inject all the samples, so you have to split your sample and make many injections in sequence, and that the auto injector is a relatively cost-effective way to do that. Next slide, please. Just to finish off, I just want to mention that we have something called an easy prep. So if you are someone who mainly does Flash HPLC, Flash chromatography, and occasionally needs to do a preparative separation, the easy prep is a hybrid system which can do both. It doesn't have the performance of the dedicated prep system, but does enable you to do prep separations from 20 to 50 millimeter columns. Next slide, please. Thanks. So it's a hybrid system, flow rate less 200 mils per minute. You got up to 240 bar with the prep system, 13 bar with the Flash system. So to summarize, we've got a product family available for Flash and preparative HPLC. All the systems you basically use the same very simple software, and all have the same safety features. We've got a range of different detection options available. We have automation available for the preparative HPLC, as I mentioned, the safety features are very important and are present in all the systems, and they all take a small amount of space. Laboratories seem to be getting smaller, but they have more and more instruments within them. Next slide, please. Just want to mention, I just touched on some applications, but there are many on our website in this link to application notes or technical notes, which you can find if you go to the Teledyne Isco website. And if you open up one of our applications, the final slide now is on tocopherols. So next slide, please, Esther. And if you pick one of our application notes, this is what it looks like. This is a purification of tocopherol, which is vitamin E, I think. Thank you very much for your time. Sorry I've overrun a bit, but if you have any questions, please let me know. Thank you.
Many thanks, Philip. Ya estoy escuchando. Ya sin pasarnos a responder las preguntas, pasaremos a responderlas, pero bueno, creo que nos hemos comido mucho el tiempo, así que lo mejor es que si tenéis alguna pregunta, nos la hagáis llegar a través del correo electrónico, mi teléfono, correo general de Vertex. Muchas gracias por vuestra atención y esperamos que haya sido de vuestro agrado.